Section 2.2 is on proving angle relationships. So up to this point, we've used inductive reasoning to explore some angle relationships, and what we mean by that is that we've looked at some examples and noticed some patterns. We've assumed that these patterns hold true for all possible cases. We can prove, however, using deductive reasoning, which is like basically a series of steps, that these properties hold true for all possible cases. So in proving these relationships, we're going to start off with two properties that we're going to kind of base all the other properties on. And the two that we're going to use are that we're going to assume that corresponding angles are equal, that we know that one is proven, and that vertically opposite angles are equal. So those are the two building blocks we're going to use to prove the rest of the properties that we talked about in section 2.1, in particular those for the parallel lines. So a particularly useful property to help us prove our angle relationships is what is called the transitive property. And this essentially says that if A equals B and B equals C, then A has to equal C. And it's just basically common sense because both of them are equal to the same thing, B. So therefore, if A is equal to B and C is equal to B, then it makes sense that A equals C. The other thing we're going to do is basically organize our work in a two-column type proof where we have statements in the left column and the reasons listed in the right column. So let's just try a couple of examples now. So the first one we're going to prove is the property that when a transversal intersects a pair of parallel lines, the alternate interior angles are equal. So this one is kind of started for you. You just have to put the reasons in. So the statement that's given to you first is angle 3 equals angle 2. And so the reason why we know that that's true is one of the building blocks we talked about, which is that the vertically opposite angles are always equal. So we'll just write vertically opposite. I'm just going to abbreviate that. Angles are equal. And then 2 equals 6. And the reason we know that is because 2 and 6 are both on the same side of the transversal, both above the parallel line. So that means they're corresponding angles. And corresponding angles of parallel lines are equal. So that's the one we said we're going to assume we know is true. So therefore it follows then, if we put those two things together, that if angle 3 equals angle 2 and angle 2 equals angle 6, then angle 3 has to equal angle 6 because of the transitive property. So when doing that now, we've proven what we started out to prove, which was that angle 3 and angle 6, which were alternate interior angles, are equal. And that's the end of our proof. Okay, example number 2 says prove that when a transversal intersects a pair of parallel lines, the alternate exterior angles are equal. So this one we don't have the statement, so we've got to come up with the statement. So we'll kind of start it the same way we did the other one. We've got some angles drawn in there for you. So the alternate exterior angles that we're trying to prove would be, I'm just going to write that on the side so you know what we're trying to get. We're trying to prove that the alternate exterior angles, which would be angle 1 and angle 8, so we're trying to prove angle 1 equals angle 8. So what can we prove angle 1 equal to? And that would be basically that angle 1 equals angle 4 would be one possible thing we can say about angle 1 because they're vertically opposite angles. And then we can say angle 4 equals angle 8 because they're corresponding angles. They're both on the right side of the transversal and both below the parallel lines. So corresponding angles, that's my angle symbol with apostrophe S there. Corresponding angles of parallel lines are equal. And again, by the transitive property that if 1 equals 4 and 4 equals 8, then angle 1 has to necessarily equal angle 8 by the transitive property. And therefore we've proven that the set of alternate exterior angles of those parallel lines are equal. And we can do a similar proof to prove the other set of alternate exterior angles are equal as well. But we're just going to use one for now. Okay, so the next example is proving that when a transversal intersects a pair of parallel lines, the same side interior angles are supplementary, which means that they add up to 180 degrees. So again, these statements are given for you and you just have to state the reasons, because this proof is a little bit different than the last one we did. So the first thing they've got there is that, well, what can we prove is 180 degrees? And we can prove that angle 1 plus angle 3 is 180 because they form a straight line or a straight angle. Straight line or straight angle, whichever one, because the straight line or straight angle has a measure of 180 degrees. So if angle 1 and 3 together form a straight line or straight angle, they have to add up to 180 degrees. And we know that angle 1 equals angle 5 because they're corresponding angles of parallel lines. And they have to be equal. So therefore, what we can do now is if 1 and 3 add up to 180, but 1 is the exact same thing as 5, what we can do is basically replace that 1 with the 5, because we know 1 and 5 are equal. So that gives us the new statement that angle 5 plus 3 has to equal 180. And that's just using a substitution there. Substitution of angle 1 equals angle 5. Then we can replace the 1 with 5 and get a statement that 5 plus 3 is 180. So therefore, we can basically say that those same side interior angles, angle 5 and angle 3, add up to 180. Right, the next example is a diagram of a cell phone tower, which is made up of a lot of straight lines that we're going to prove are parallel. So it's asking you to use the angle measures provided to prove that line CG, which is this one, and line BF, which is this one, and line AE, which is this one, are all parallel. So if we look at the diagram, we can say that, look at the two lines CG and BF and the transversal BG that crosses over those two lines, right here. Can't draw a straight line, sorry, diagonally, whatever way this pen works. So looking at line CG and BF with the transversal BG, we can see that there's two angles that are in the corners of the Z that have a measure of 35 degrees, and they are alternate interior angles which are equal. So angle C, G, B, and when you're naming an angle using the three letters, the middle letter is always the one where the vertex of the angle is, or that pointy part, the corner of the angle. So angle CGB equals angle GBF equals 35 degrees. If you want to write that in, you can. And that's given. So since they're both 35 degrees and they're alternate interior angles, then we can say that CG has to be parallel to, line CG has to be parallel to line BF, because alternate interior angles equal implies parallel lines. And then similarly, we can move to the last set of lines, the BF and the AE set of lines, and look at the transversal from B to E that crosses over those two lines. And we see that there's another set of alternate interior angles marked 22 degrees that are equal because they're in the corners of the Z formed by the parallel lines BF, AE, and the transversal BE. So we can say that angle FBE is equal to angle AEB is equal to 22 degrees. That's given to us. So therefore, the line, what was it, BF? Line BF is parallel to line AE because, again, alternate interior angles imply parallel lines. And therefore, if CG is parallel to BF and BF is parallel to AE, then CG, oh, I made my G first, doesn't matter if I say CG or GC actually. CG also has to be parallel to AE by the transitive property as well. Because both of those lines are parallel to BF, then therefore they have to be parallel to each other. So we've proven that all three lines are parallel to each other. All right, the next proof is kind of a lead into the next section actually. But it's basically proving that the sum of the angles of a triangle is 180. It's kind of a neat little proof. So the statements are given to you here, and we've got the diagram provided, and what happened in the diagram is it just basically took any triangle and they constructed a line through the top vertex of the triangle so that it was parallel to the base of the triangle, right here. So basically construct a line through the vertex at the top of the triangle so that it's parallel to the base of the triangle. And then you can proceed to do this proof. So once we construct that line through the top vertex of the triangle, we see that it forms three angles, angle A, angle B, and angle C. And those all have to add up to 180 because they form a straight line or straight angle. Because if angles together form a straight line or straight angle, they have to have a measure of 180 degrees altogether. Angle A has to equal angle D then, because we constructed the lines parallel. Angle A and angle D would be considered alternate interior angles. They're on opposite sides of the transversal, inside the parallel lines, in the corners of the Z, whatever way you want to look at it, but they are alternate interior angles of parallel lines. So therefore they're equal. And by the same reasoning, C and E have to be equal using that other transversal that crosses over the two parallel lines that we've got in our diagram. So again, angle C equals angle E because alternate interior angles of parallel lines are equal. So now we go back to the statement that we had at the beginning, that A plus B plus C, and this is what we're going to work with. But we know that if A equals D and C equals E, we can basically make a substitution of A with D and C with E. So therefore, this is like substitution. Instead of saying angle A plus angle B plus angle C, we can say angle D plus angle B plus angle E by using that substitution 2 times. So now, instead of, if they're equal to each other, if A, B, and C equals angle D, B, angle B, and angle E, then we can replace this up here with angle D, B, and E, and that gives us the statement that angle D plus B plus E equals 180. And that would be basically a way to prove that the sum of the angles of the triangle, which in our diagram were angle D, angle B, and angle E, had to add up to 180. Kind of a neat little proof. Anyway, there's some examples there at the bottom of the page that you can try in your textbook to help go over some of the concepts we learned in this section.